So this is a typical example of the mean value theorem, where I say to find the C value predicted by the mean value theorem. Okay. So in this case, I gave you a graph, but you actually don't need a graph to do this problem. The graph is just to sort of guide your intuition as you work through this problem. So let's go ahead and do that now. We're asked to find the C value predicted by the mean value theorem for this given function on this given interval from 0 to 2. So let's just go ahead and look at this function from 0 to 2. That's the interval that we're talking about. And so this would be the point on the left-hand side, and this is the corresponding point on the right-hand side. So in the mean value theorem, what we would do is we would look at the slope of the secant line, right? There's the slope of the secant line, connecting the two endpoints. Okay. Now, what is the C value that the mean value theorem predicts? It predicts that there is a C value, some X value, on the interval between 0 and 2, somewhere in between these 2 points, where the slope of the curve, the slope of the tangent line at that point, matches the slope of the secant line. Do you see where it is on this graph? I'm not exactly sure where it is, but it might be right about here. That might be my C value. Right about there. Why is that? Because if I go and draw the tangent line at that point, notice that the tangent line matches the slope of the secant line there. The question is where is that C value? So that's the question. The question is to find the C value predicted by the mean value theorem. And you can do this problem without having to look at the graph. And in fact, looking at the graph doesn't actually help you because you're still not sure where it is. You just know it's somewhere between 1 and 2. So let's go ahead and find that C value. So to do that, we just simply remember the expression that the instantaneous rate of change at C is equal to the average rate of change over A and B. So what I'm going to first compute is I'm going to compute the slope of the secant line first, which is f of B minus f of A all over B minus A. So in this case, B is being played by 2 and A is being played by 0. So that gives us f of 2 minus f of 0 all over 2 minus 0. So that gives us, let's see here, 6 minus 0 all over 2 minus 0, which gives us a slope of the secant line of 3. So folks, you're guaranteed to have a problem similar to this one, not this same one. You're guaranteed to have a problem similar to this one on your next exam. I have a lot of people that get to this point and they think that they're done with the problem. Did we find the C value yet, folks?
No.
No, all we found is that the slope of the secant line is 3. That's all we found so far. So what do we want to do next? Well, we want to go ahead and find the C value, the place on the function where the slope of the tangent line is also equal to 3. So let's take the derivative of this function. The derivative of this function is 3x squared minus 1. And now I'm going to set the instantaneous rate of change equal to the average rate of change. So again, this is the instantaneous rate of change. And what did I just do? I just set it equal to the average rate of change. Okay. Folks, everything I've done so far hasn't required us to use the mean value theorem. We've just kind of been setting up, but we could always find a derivative. We could always find the slope of the secant line. Where does the mean value theorem come into play? Let's look back up at the statements of the mean value theorem. It says, suppose f is continuous on a closed bounded interval and differentiable on its interior, then there is guaranteed to be a C value, so that this piece here is true. So let's run through and make sure we've met the conditions of the mean value theorem. And you do need to always check this. I can't give you full credit if you don't confirm to me that you've met the conditions. So, f is continuous. Actually, this function's continuous on minus infinity to infinity, but specifically for our problem, it's continuous from 0 to 2. So that's what we're checking. It's continuous on the closed bounded interval. And f is differentiable. Again, in this case, f is actually differentiable everywhere, but it's certainly differentiable on the interval from 0 to 2, the open interval. So the mean value, that was 2, I guess, so the mean value theorem applies. Okay. So where does all of this come into play? Well, I'm now going to try to solve this equation right here. I'm now going to try to solve that equation. Do all equations have solutions? I'll let that stay there. Do all equations have solutions? Have you guys ever gone to solve an equation before and found that there was no solution to it?
Yeah.
Yeah. I think it's fairly common in math. When you go to solve an equation, it turns out there's no solution. Okay. This equation has a solution, though. I'm not scared. Why do I know this equation has a solution? Because the mean value theorem guarantees this equation has a solution. So let's go ahead and do so. I'm going to take this equation. I'm going to try to solve it. I know it has a solution, though, because the mean value theorem guarantees it has a solution. Even though it's a quadratic, right? Sometimes when you go to solve a quadratic, you get imaginary roots. Am I going to get imaginary roots on this problem? No. I know I'm not going to because the mean value theorem applies here. So let's go ahead and solve it. We get 3x squared minus 1 is equal to 3, or 3x squared is equal to 4, or x squared is equal to 3/4, or x is equal to plus or minus the square root of 3/4, or, oh, did I have a mistake? Thank you. Thank you, Stephen. 4/3, thank you. And so we get x is equal to plus or minus the square root of 4/3, or x is equal to plus or minus the square root of 2 over the square root of 3, distributing that square root to the numerator and denominator. Only one of these lies in the interval between 0 to 2, but that's good enough. That's good enough to find that c value. So that is our c value. Okay, if you want a decimal approximation on that, you would find that 2 over the square root of 3 is approximately 1.15, which fits with where it looked like our c value was on the original problem.